compound was created by myself and my brother after we have been in the industry for a few years, and we saw a building code that wasn't up to scratch. It was quite embarrassing compared to the rest of the world, and we saw there's heaps of room for improvement. We know that energy efficient housing is very accessible and can be affordable if you do it right. Yeah.
Sweet. Welcome to Moonlight. The point of this series is we wanted to bring you on the journey of our goal of achieving a passive house, and spoiler alert, we don't actually achieve the passive house standard. You'll see that it's possible to build a house like this to a budget, and you don't necessarily need to achieve the passive house standard to build a home that's very energy efficient and healthy. The entire build's going to take about 12 months. The video series is going to involve 4 to 5 videos, and we'll be releasing videos every 2 months. And these videos are going to showcase the whole process from the start to the finish.
We wanted to show that it was possible to build such an energy efficient and high performing house when the site was so difficult.
So the Moonlight build for the compound job, probably the biggest challenge comes back to that orientation of the site. And it was the biggest thing that we noticed as we were doing the energy modelling and influenced how we actually changed the design as we went along.
In the preliminary design stage of Moonlight, we had Team Green do a modelling exercise on the CAD. What that told us is how much sun was going to be going in through different windows. Can we move windows? Can we make them bigger, smaller? How minute changes in the aspect of the house can affect the heating.
The views on the site are predominantly sort of to the east or the northeast, and that's the way that the land slopes as well. So you're sort of thinking that's where you want your most windows, but the sun is actually off to the side, which is where there's another house right here. And then beyond that in the distance is the mountains and trees and so on. So that's also cutting off some of the sun that's coming into the building.
Typically, you'd have an architect that would create a design for solar, but they wouldn't model a house, so they wouldn't have an exact answer on how big eaves need to be, how small, or the location of windows, and how that impacts on the kilowatts of heating and cooling requirements.
We're coming into the cooler months now. We're in May, and the sun just slowly moves along this ridgeline here of the Cardrona Valley in the Crown Range, and it'll just move across and rise about 8:30, and then arc its way quite low over Coronet Peak, over Mount Dewar over here. The orientation of the home, if you look down here, you can see it's a basic square formation, 10 by 9 two-storey house, where the front living is facing east, northeast. The difficult thing about Central Otago's climate is it's very cold in winter and it's very hot in summer. So we've got to try and balance these two in the design of the home. We want to harness the sun's heat in winter and bring it into our living area, which we have by a low overhang at that eastern face. And then we want to block out the sun when it's at its harshest in the summer. So we have a 2-metre overhang protecting us when the sun's at its northern and northwestern aspect, and stopping as much of that radiation coming into the living room. So currently we're at foundation stage. We've got our footings dug for the building. We are prepping our footings. Watertight systems are in, waterproofing, the first detail along this wall where we've got our first pour, and then we'll build our blocks up and then continue on with our foundation prep. I was frothing yesterday. This detail I've kind of made along here, because the way the Nudura is detailed normally is it just sits directly on this footing here, and then you have a thermal bridge of all the concrete in the footing coming up the wall and into your slab. So as your slab heats up, and then in winter when it's cooling, this will just draw all the heat out of your slab. So it's like a thermal bridge. And then now we've put this XPS green foam, which has a compressional strength of 360 kPa. So my engineer's more than happy for it to be placed here, and now we've reduced all our thermal bridging just to these point bridges through the rebar. So like a huge improvement on performance. It just means as we install it, like this is all just set out like Lego. You can compare it to where we exactly want this to slot onto. So now as we measure and install, we know we're, down to the mill in the right spot. So for couple of hours work of adding this, we've got, in minimal costs, we used 1.5 sheets of this. We've got a huge increase in performance, increase in efficiency on the install now, and we're set up today to just smash it in and not really have to think about too much. So yesterday I was just pretty stoked. The reason we're using this hot knife is for waste. The downfall of polystyrene, which is also its benefit in construction, is its durability, like it doesn't break down. So in terms of waste, it's really important to control that. So we'll cut it with a hot knife so we don't get as much of the flaky stuff. And then we can put all this in a bag, which we have over there, and recycle it at a factory which makes polystyrene products. So in terms of what we're doing here is we're building up our foundation walls, and the main goal is a fully insulated foundation or slab. So we've got our Nudura block walls which encapsulate concrete with 60 mil of polystyrene either side. So then that insulates all that concrete, and we'll bring that up to our finished floor height on these walls and perimeter walls of the foundation. And then we can prep our slab, which we bring our grade up, and then we insulate above that grade and pour our 100 mil topping slab on top of all of that. So this way we have a fully insulated foundation.
Insulating slab isn't in the code at the moment. It's something that we're seeing a lot more of in standard builds because people are seeing that it's really important, but it's still not part of the building code by any stretch.
So it's 1st of June. We've been building for 7 weeks since we tore the topsoil off this site. We've done our landscape retaining walls that tear us down in front of the house. We've done our excavation, poured our footings, poured our perimeter Nudura block, and now we're into the foundation prep for the house. Today we'll talk about thermal bridge-free construction, which is one of the 5 principles of Passive House, and the importance of getting the details right during the foundation. A thermal bridge is where cold can come in or heat can conduct through a surface of a material and its makeup. Yeah, so our foundation is made up of 2 layers of 50mm extruded polystyrene foam. We're using gold foam from a New Zealand supplier through our merchant at Placemakers. It's a R1.8 and we have 2 layers, so we've got an R3.6 in the slab. So that's the makeup of our insulation slab here. 2 layers because we cross-lay the different layers. So if we just did a single layer, we'd have a weak point through our join. So this way we really take care of any thermal bridging through the joins. You might be wondering what these trenches are through here. So these are thickenings designed by our engineer, and they're taking load of frames and beams that transfer through our building and up into our roofs. And when we pour the concrete, this here is going to be a thickening full of concrete and reinforcing. So a challenge with that design is how do we maintain thermal bridge free construction when you have a structural element like these thickenings. So this is where we're going to use green foam product. So this product has a 360 kPa compressionable strength, and my engineer is happy for me to use this at the bottom of our thickenings. We've gone a little bit lower, and then that has the compressionable strength to run through there and thermally breaks our foundation. So if we didn't have the green foam XPS in this thickening, the concrete would be just going down straight onto ground, and concrete being a conductor, then that would incur heat loss in the winter months. The really important part about thermal bridge free construction is where our different construction elements meet and that thermal break is continuous throughout the whole house. So here's a good example. We've got our 2 50mm layers of XPS here, and then that's tying into our insulated concrete form, our Nudura block. And as you can see, this layer comes all the way through, and it's meeting our Nudura block. Then we know that that runs all the way down. We have a thermal break at the bottom of this concrete and then comes up here. So when we fill this with concrete and have our whole slab, we know this whole foundation, whole slab is thermally broken. It's 7 AM, it's the 8th of June. We are pouring the slab today. It's going to be a polished concrete slab with 13 and 19mm river stones and a black oxide colour. It's been a long night getting everything for the last final checks, but we're good to go. Right, it's Monday the 21st of June, week 10 of construction here at our Moonlight project, and we're just going to brief on everything now that our slab's poured and our walls going up, and we can look at all these critical junctions. So here we're going to have a timber framed wall here, and then we have this wall here, and then this is our slab, and all the materials are going to meet with a thermal break continuous from our slab below grade and all the way up. Now this is where all the magic happens. Now we've got this big thermal mass in our concrete slab. We've insulated it and we have 0 thermal bridges throughout the whole construction of our foundation. So now when the slab gets up to an ambient temperature of about 20 degrees and our inside living space is the same, we're not going to have any heat loss through our foundation. So I thought we'd just recap why we use this product, Nudura, in the polyblock form. Being on a hillside, we need to retain some of the hill as we build into the hillside. For us, we only need to retain a small amount on this wall and the back wall, and we get the required strength from the engineering And with this form, we get a continuous thermal break and a continuous insulation layer. This is where building to the passive principles, but within your budget, is really important. We've got our south walls built into the hillside. They're a retaining, made out of Endura block. And then we've got our north-facing walls. With the orientation, we've got all that heat gain from the sun, and we're going to go back to traditional framing through here. And this is where we are looking at our budget and ways to meet that. You know, in a perfect world, I would have done Endura block all the way up. It's a really good product, but we can work with our budget and have a happy medium.
The thing with the Moonlight build is that we originally set out to build a passive house, like that is the goal. It means you're ticking almost every box. And we also have our own limitations, like our budget. And so it's been really interesting going through that process and seeing what we could afford and dialing things back where necessary.
The compound building is just below 30 kilowatt hours per metre squared per annum for its heat demand. And that puts it into what Passive House class as a low energy building. And for our region, depending on the building, most buildings are somewhere between 150 kilowatt hours to up to sort of 250, 300 if they're really inefficient, and they were designed to building code minimum standards. So we've already made that 5 times better than it could have been, at least 5 times better. If they were at Passive House standard, they'd be at 15. So in some ways you could say you start to get diminishing returns as well, because you get to the point where you've made this huge jump from 150 down to 30, and then 30 to 15 is a much smaller jump, but it's actually quite hard if you've got all these other things working against it, like the orientation that I was talking about, to make that final push in terms of extra cost and the things that you would have to do to bring it to that standard. So Passive House was developed 30 plus years ago in Germany, and it was a specific place and time that it was developed. And the point that was agreed was the standard, which was the 15 kilowatt hours. Rather than that being 0, is that it was still considered cost effective to do that. So it wasn't taking it beyond the point that it was going to cost the majority of people too much to achieve that standard. What you don't necessarily have here at this place and time is an agreement that still is cost effective to reach that point, because it's so costly to build in New Zealand, particularly in our region. It's really costly to build. So that's often why we don't get all the way to the standard, is because of that. So you know that you've also started at such a low point in New Zealand. You've started at a point where buildings are really inefficient. So once you bring it way, way above that to, like Josh and Drew have done, to the 5 times better, it starts to make less sense to try and push it, unless you wholeheartedly said this building has to be certified Passive House.
In summary, we've got a thermal bridge-free foundation and slab. Now we've got really good insulation throughout. We've worked with our engineers throughout the whole process, so if there was anything that they maybe hadn't done before or that I wanted to improve, we just worked through the numbers and they were happy with the changes. So nothing's impossible, and the numbers don't lie, so you can achieve this anywhere. Critical junctions we need to focus on as construction progresses.